Today's topic, 1.3, graphs of functions. We're going to look at two key vocabulary. First one, the vertical line test. The vertical line test is, or states, or can test to see if something is a function if a vertical line intersects the graph of a function or the graph of a relation, if a vertical line intersects a relation at only one point, then it is a function. We'll look at this in a couple minutes, how we use the vertical line test. Piecewise function. Okay. We'll get the definition down, and then we'll look at some piecewise functions in just a minute. It is defined by at least two equations. Now there could be more, but it has to be at least two equations over a specified range, which means there's boundaries on each equation. We'll look at piecewise functions a little bit more in a few minutes. Let's look at domain and range for graphs that we haven't seen before. Here's kind of this crooked little line here. In this first one, we have this crooked line. In the second one, we look like we have like a little shelf. Notice on both graphs, this one, both ends are solid circles. So that function starts and ends at a certain place. This function, okay, or this graph has a solid circle at one end and an open circle at the other. And we'll talk about how that is. So when we write the domain for this, let's name the point. This point is -4, -4. This point is 3, 5. Okay, so again for our domain, after we've named our points, what we want to do is look at our domain or our x values. So we look at our x values. Where do our x's go? It goes from -4 to 3. So the lowest x value is -4. But since there's a solid circle, we're going to use less than or equal to. And then the greatest x value is 3. So my domain goes from -4 to +3. When I look at my range, my lowest y value is -4, and my greatest y value is 5. So when I look at it, my y has to be greater than or equal to, because it's a solid dot, -4, but then it's less than or equal to 5. So it's between -4 and 5, the lowest and highest y value, which makes it a little tricky when we come to the next graph here. This point, let's name it 3. This point 4, -1. This point is -3, 4, and this point is, oh wait, that's -2, 4, and this point is 3, 4. So my domain, again, I'm looking only at my x values. I'll write the x values here. here. And I'm going to take it, and I'm going to say my x-axis, my lowest x value is -4. It's a solid dot, so it's going to be less than or equal to. So I know my x has to be greater than -4. But now I have an open circle. So that means it's not going to be equal to 4. It's just less than 4. The range is a little tricky. I don't use the two endpoints for my range here. Okay? In this case, for my range, I'm looking at my lowest y and my highest y. Okay? My lowest y, okay, and my highest y. So my lowest y goes from -3. Even though there's not a dot there, it continues this direction. So it's an implied solid circle. So if my y's go from, if I'm looking at it vertically, my y's will range from -3 to 4. Here's the vertical line test that we were talking about. Basically what you're going to look at, let me pull up a ruler here really quick. Let's see if I can turn this. I don't think I can turn it. Never mind. Okay, basically what a vertical line test is. If I take a pencil or a pen and I draw a line all the way up and down through the entire function, it only intersects at one point. So for each input, or x value, there's exactly one output. So in this case, it's going to be a function. Again, for each input, if I draw a vertical line through this one, this would be a function. On the next one, if I draw my vertical line, it intersects in two places. So it's a relation, but it's not a function. Because for each x input, there are two outputs. So for this x input, there's 1, 2 outputs. So this is not a function. On your own, I would like you to do the next 3 on your own, and we'll check them tomorrow in class. See how well we did with the vertical line test. Okay, so now let's look at piecewise function. This is a piecewise function. Remember I said it has at least 2 equations? In this case, there are 1, 2, 3 equations. Okay? Defined by a specific piece of the domain. There's the specified, this column is called the specified domain. So, in this piecewise function, if x is less than 0, I use this function. If x is between greater than or equal to 0 but less than 2, my function is equal to 4. If x is greater than or equal to 2, my function is x squared plus 1. So when I go to evaluate f of -2, I'm going to use the first equation because -2 is less than 0. So I find f of -2 and I plug it in or substitute into the first equation. So f of -2 is equal to 0. If I'm finding f of 2 and I look at this second, I know it's not less than 0. But is it between, it's greater than or equal to 0, but is it less than 2? No. So I go to the next one. 2 is greater than or equal to 2. So 2 greater than or equal to 2, where it's true. So I substitute it into the third equation. And I get 4 plus 1. So f of 2 is going to equal 5. Evaluating a piecewise function. So let's try this one. F of -2. Where does -2 lie? In which equation? It lies in equation, in the first equation, because -2, again, is less than 0. So I'll substitute it into the first equation. So F of -2, let me erase that and write that quickly. So F of -2 equal to 5 minus 2 times -2, which would be 9. F of 1/2, it's between 0 and 1. So F of 1/2, now there's nothing in this equation 2 to substitute in, so anything between 0 and 1 is just equal to 5. And then if I'm looking at F of 1, 1 is greater than or equal to 1, so I'm going to evaluate it by substituting it into the third equation, which is also equal to 5. So let's evaluate. Last example, we'll be looking at graphing our piecewise functions. How we want to start this is we have to graph based on our domain restrictions. Okay? Based on our specified domains. Okay? So what I want to do is I'm going to first start with I'm going to start with F of 1 into the first equation. I'm going to evaluate, I should say, not sub. I'm going to evaluate F of 1. With the first equation. So what I do is I substitute it in. So 2 times 1 plus 3 equals 5. So my ordered pair is when x is equal to 1, that's my input, my output is 5. However, because it says it's less than 1, okay, less than 1, I'm going to then have an open circle at that point, and a slope of 2, right? The slope of 2 from my equation. Okay, so at 1, 5, we have an open circle and a slope of 2. Well, now if I plug in 0, because 0 is less than 1, I would end up with 3, which is a slope down 1 over 2. And I draw my line. So I'm going to take a point that's less than 1, that's less than 1 because it's in my specified domain, and I get 3, so I have another point at 0, 3. I've only dealt so far with my first equation. I'm going to do the same thing with my second equation. I'm going to evaluate F of 1. So that's a -1 times 1 plus 4, so that's going to be 3. However, because it says it's equal then, at the point 1, 3, I will have a closed point in that specified domain, say 2. So I'm going to evaluate f of 2, specified domain. It says it's greater than 1. So I pick 2. So when I evaluate it for 2, it's going to be 2. So I'm going to use the point 2, 2. Let's plot that. 2, 2. And it does have a slope of -1.